In this video, we'll be looking at something called end behavior and its corresponding arrow notation. End behavior is specifically the way that we're going to algebraically or more notationally identify what the function is doing as it goes off towards either positive infinity or negative infinity, be that in terms of x's or in terms of y's. The end behavior must be identified in terms of both x approaching positive infinity as well as x approaching negative infinity. And the idea is we want to know what is y doing as x does those things. The other kind of end behavior that we may refer to is specifically ones where we're talking about vertical asymptotes. So when we look at this function in its basic notation, a vertical asymptote of this function, we're going to start with identifying its domain. Its domain is x cannot be equal to 0. Identify its discontinuities. Its discontinuities are x equals to 0. And that discontinuity will either be a whole or it will be a vertical asymptote. Again, these are the abbreviations of previous videos that we've already done work on. So because the factor on the bottom can't cancel out with anything on top, we don't have a whole, and therefore this thing is a vertical asymptote. Every vertical asymptote will also include the concept of the end behavior. We want to be able to algebraically show or notationally show what the function is doing around that vertical asymptote. In this case, I want to know what is what is y doing as x approaches 0. I also want to know what it's doing specifically in both directions. So in terms of the notation we use for that is we say x approaches 0 specifically from the right, and x approaches 0 specifically from the left. So the right side is coming in from the positive values, coming in from the positive side, coming in from the positive values, and then the 0 to the negative, again, not exponent, but notation. That notation there refers to x approaching 0 from the left. So in that case, in all four of these circumstances, we want to know what is y doing. Okay, for us to do that, we're going to have to pick some values and randomly graph. I wouldn't say randomly, but I would say systematically be able to sketch this graph before we can do this. Now I know that 1 over x has a vertical asymptote at x equals 0. I know that specifically from, again, the work that I did here. The next thing I'm going to do is identify either a horizontal asymptote or a slant asymptote. In terms of the horizontal asymptote, because the power on the top is smaller than that on the power than the bottom, y equals 0 is a horizontal asymptote, and if I have a horizontal, I don't have a slant. If I have a slant, I don't have a horizontal. So I know I have a horizontal asymptote at y equals 0, and then what I'm going to do is I know that this function is supposed to be guided by these two dotted lines. What I would recommend is finding a couple of points. Say at x equals 1, what is that value going to be? Well, when I plug it in, I'm going to get back the value of 1. If I were to do negative 1 at the same time, I'm going to get a negative 1 over here as well. You could also plug in a few more values. Say if I plug in 2, I'm going to get a 1/2. So it's going to be a little bit closer to the x-axis when I plug in 2. Same thing's going to happen over here when I plug in a negative 2. I'm going to get a negative 1/2, which is going to be closer here. This should give you an idea of what the function is going to do, give or take. It's supposed to approach these dotted lines, so if I draw these two dots together, this should approach that dotted line in that direction. And again, we can't cross these vertical asymptotes. With the way that they're built, we can't actually draw a line passing them because the dotted line is supposed to guide the function. So that's going to happen here as well. We're going to go ahead and approximate it that way, and it's going to approximate that way. Now, if for any reason we're not comfortable with the way that this graph is going to look, then plot more points. Again, plug in values getting closer and closer to 0 from the negative side, plug in values getting closer and closer to 0 from the positive side, plug in more values over here and more values over here to verify that this is actually the way that the function should appear. Now once you've got this graph listed, the idea is, what does the function do? Well, let's go ahead and trace the graph as x approaches infinity. So as x approaches infinity, as we go in this direction, your y value is getting closer and closer to this horizontal asymptote. So the y value is actually approaching 0. If we look at x going towards negative infinity, again, the same concept now. We could start all the way over here, and we would trace this line going all the way up. We're not yet at negative infinity, so we would go ahead and jump down here and go ahead and continue to follow the line until we approach the y value of this horizontal asymptote, once again being 0. Now as x approaches 0 from the right and x approaches 0 from the left, if we're approaching from the right, again, we're coming in from the positive side, these two things change the way that we approach that value. So we're approaching this value in the middle, and the graph again, as we get to closer and closer to that value, is going to get larger and larger, and therefore approaches infinity. If we do it from the left side, again, approaching from this direction here, you'll notice that the graph is going down towards a negative infinity. And that's the notation we would use for that end behavior information. For us to, again, identify any end behavior and very clearly write this out, we're going to have to see the graph of the function. It's really not easy to identify what the function is doing in terms of the end behavior just by evaluating some values in here and getting some algebraic information from the function.